Hi students, welcome back. In this video, we've solved all the 5-mark questions. This question, if z is equal to x plus iy is a complex number such that modulus of the given value is equal to 1, show that the locus of z is a real axis or y is equal to 0. So let us write first what is given. Given modulus of z minus 4i divided by z plus 4i is equal to 1. Let us take let z is equal to the complex number x plus iy. Now substituting x plus iy, we get modulus of x plus iy minus 4i divided by z plus 4i. Z, we substitute the value as x plus iy plus 4i is equal to 1. Now we can write this as modulus of x plus I into y minus 4 divided by modulus of x plus I into y plus 4 is equal to 1. Now taking this term to the right, it can be written as modulus of x plus I into y minus 4 is equal to modulus of x plus I into y plus 4. We know the modulus of z is root of x square plus y square, that is root of real part square plus imaginary part square. So the real part is x square plus the imaginary part is y minus 4 the whole squared is equal to root of x squared plus y plus 4 the whole squared. Now squaring on both the sides, in order to remove the root, we square on both the sides. So squaring, we get x squared plus y minus 4 the whole square is equal to x squared plus y plus 4 the whole squared. Expanding the equation, we get x squared plus y squared plus 16 minus 8y is equal to right hand side x squared plus y squared plus 16 plus 8y. So on both the sides, x square, y square, 16 gets cancelled. We get 16y is equal to 0, which implies y is equal to 0. Y is equal to 0 is the equation of the real axis. Therefore, we say the locus of z is the real axis, that is y is equal to 0. The next question, show that 2 plus I root 3 whole power 10 minus 2 minus I root 3 whole power 10 is purely imaginary. We know the result if z is equal to z bar, then which implies that z is real. But here the question is, show that it is purely imaginary. What is the condition for purely imaginary? If z is equal to minus z bar, then we say that z is purely imaginary. So here in this problem, we have to prove that the given z is equal to minus z bar. Now for that, let us take, let 2 plus z is equal to the given question. Z is equal to 2 plus I root 3 whole power 10 minus 2 minus I root 3 whole power 10. Now our aim is to show that z is equal to minus z bar. Now we find what is z bar. Now z bar can be written as is equal to 2 plus I root 3 whole power 10 minus 2 minus I root 3 whole power 10. Now, taking the conjugate of this, it can be written as 2 plus I root 3 whole power 10 conjugate minus 2 minus I root 3 whole power 10 conjugate. Conjugate, we know if z is equal to x plus iy, then its conjugate z bar is equal to x minus iy. Therefore, this conjugate 2 plus I root 3 whole power 10 conjugate can be written as is equal to 2 minus I root 3 whole power 10 minus conjugate of 2 minus I root 3 whole power 10 can be written as 2 plus I root 3 whole power 10. Now coming to this question, we have taken z is equal to 2 plus I root 3 whole power 10 minus 2 minus I root 3 whole power 10. Now taking the minus sign outside, we get minus of taking this term 2 plus I root 3 whole power 10 minus 2 minus I root 3 whole power 10, which is nothing but is equal to minus z. So here either z bar is equal to minus z, or it can be written as z is equal to minus z bar. Therefore, we say that z is purely imaginary. Points is closest to the point 1 plus I. So for this we use the distance formula. So the distance from the point 1 plus I to the first point 10 minus 8I is modulus of, we know that the distance between the two given points Z1 and Z2 is given by distance between Z1 and Z2. We know what is the distance formula. Distance formula is given by mod of Z1 minus Z2. So the two given points are 1 plus I and 10 minus 8I. So now that is equal to, it can be written as this is equal to modulus of Z2 minus Z1. I take so 10 minus 8I minus 1 plus I, which is equal to modulus of, take the real parts together, 10 minus 1 minus I into 8 minus 1, or we can take, I have taken the minus sign out, so it can be written as 8, here one minus, so becomes 8 plus 1. Now this is equal to mod of 10 minus 1 is 9 minus 8 plus 1 is 9, mod of 9 minus 9i, which is equal to 9 into mod of 1 minus I, which is equal to 9 into root of 1 square plus of minus 1 whole square. So plus 1 which is equal to, can be written as 9 root 2. Now next we find the distance between the next point from 1 plus I. So distance from 1 plus I to the next point, that is 11 plus 6I, can be written as is equal to mod of Z2 minus Z1 or Z1 minus Z2. It can be taken as 11 plus 6I minus 1 plus I. Now this is equal to modulus of 11 minus 1 plus I into 6 minus 1, which is equal to modulus of 10 plus 5I. Now this is equal to 5 into modulus of 2 plus I, which is equal to 5 into root of 2 squared plus 1, which is equal to 5 into root 5. Now finding which point is closest. This is 9 root 2 is nothing but is equal to root of 81 into 2. So 9 square 81 into 2, when I take inside the root it becomes, it's equal to 162. Next 5 root 5 will be is equal to 25 into 5, which is equal to 125. To find which number is closest to the given point, we can say that this 11 plus 6i is close to the given point. So 1 root of 125 is smaller than root of 162. Therefore, we say that 11 plus 6i is closest to 1 plus I. Another important question, if z is equal to x plus iy is a complex number such that the imaginary part of this term is equal to 0, show that the locus of z, they have given the equation for the locus. So let z is equal to x plus iy is given in the question. We write z is equal to x plus iy. Next, we take the term which is given inside. The next question is another important question. If z is equal to x plus I by, show that the argument of z minus I by z plus 2 is equal to pi by 4 is given. Then we have to show the given equation is equal to 0. We know that argument of z1 by z2 can be written as is equal to argument of z1 minus argument of z2. So we are going to apply that first here. So let us write what is given. Given that z is equal to x plus iy and argument of z minus I divided by z plus 2 is equal to pi by 4. So argument can be written as result. We can write it as argument of mod numerator separately my z minus I minus argument of z plus 2 is equal to pi by 4. Now substitute z is equal to x plus iy. We get argument of x plus iy minus I minus argument of x plus iy plus 2 is equal to pi by 4. Now separate the real and imaginary parts. We get argument of x plus I into y minus 1 minus argument of the real part is x plus 2 plus iy is equal to pi by 4. Now, argument of z is nothing but tan inverse of imaginary part by real part. So, we know that argument of z where z is equal to x plus iy can be written as is equal to tan inverse of the imaginary part divided by the real part. So, this gives us tan inverse of the imaginary part is y minus 1 divided by x minus tan inverse of the imaginary part is y divided by x plus 2 is equal to pi by 4. Y can be written as is equal to tan inverse of x minus y divided by 1 plus xy. So we applying this formula here, we get this is equal to tan inverse of y minus 1 by x minus y by x plus 2 divided by 1 plus x into y minus 1 divided by x into y by x plus 2. This is equal to pi by 4. Now, taking tan on both the sides, bracket term we cross multiply. It can be written as y minus 1 into x plus 2 minus xy whole divided by the denominator, that is x into x plus 2 whole divided by, taking this term for the LCM, we get x into x plus 2 plus y into y minus 1 whole divided by, this is whole divided by this term divided by this denominator, that is nothing but is equal to x into x plus 2, which is equal to pre-multiplied by tan on both the side, or taking tan inverse to the right side, it becomes is equal to tan pi by 4. Now the minus xy goes off. 2y minus x minus 2 is equal to x squared plus 2x, taking this term to the right, plus y squared minus y. Again this gives us, take this term to the right, we get x squared plus y squared minus x plus 2x goes to right, becomes plus 3x. Here minus y plus 2y, other side becomes minus 2y. Minus y minus 2y is minus 3y. Minus 2 goes to the right, becomes plus 2 is equal to 0. This is what asked to prove. Is equal to 0 where z is a complex number. So let us now write what is given. Z cube plus 8i is equal to 0. This gives us z cube is equal to minus 8i. Now this is equal to, which can be written as 8 into minus I. Now this is z cube is equal to 8 into minus I, or z can be written as is equal to 8 the whole power 1 by 3 into minus I the whole power 1 by 3. Now this I must be written in polar form. So how to write this I in polar form? I we know is equal to cos pi by 2 plus I sin pi by 2. Minus I can be written as is equal to cos of minus pi by 2 plus I sin minus pi by 2. Now this can be written as 2 cube whole power 1 by 3 into minus I. So this is cos minus pi by 2 plus I sin minus pi by 2. Now we can apply the De Moivre's theorem here. Before applying De Moivre's theorem, what is the working rule to solve the equation? Add 2 times of cos of minus pi by 2 plus 2k pi plus I sin of minus pi by 2 plus 2k pi. Working rule to solve the equation will be adding 2k pi. Next applying, this is to the whole power of 1 by 3. Next apply the De Moivre's theorem. Before applying the De Moivre's theorem, we simplify k pi divided by 2 plus I sin of minus pi plus 4k pi divided by 4 whole to the power of 1 by 3. So this is 2 into cos of minus pi plus 4k pi into 1 by 3. So we bring this 1 by 3 to the argument here. So this is minus pi plus 4k pi divided by 2 into 3, 6 plus I sin of minus pi plus 4k pi divided by 6. The next step for the working rule. First, write it in polar form. We have written in polar form. Add 2k pi to the argument value. Next, apply the De Moivre's theorem. Now, substituting the values for k, taking k is equal to 0, 1, 2, etc. up to n minus 1. Here n is equal to 3. Therefore, we take values k is equal to 0, 1 and 2. Now substituting the value k is equal to 0 in the given equation, we get this is equal to, and k is equal to 0, 1, 2 in the given equation. Suppose we substitute k is equal to 0. What is that we are getting? 2 into cos of minus pi plus 0 by 6 plus I into sine of 0 plus minus pi by 6. So we get when k is equal to 0, the first value will be, when k is equal to 0, the first root is 2 times of cos theta plus I sin theta can be written as cis theta. So I write it as cis of minus pi by 6, which is equal to cos pi by 6 minus pi by 6 plus I sin of minus pi by 6. You know that cos of minus pi by 6 is equal to cos pi by 6, which is equal to root 3 by 2. Cos 30 root 3 by 2. Sine of minus pi by 6. Sine of minus theta is minus sine theta. Therefore, it is minus pi by 6, which is equal to minus 1 by 2. So, this gives us the value. This is equal to 2 into root 3 by 2 minus I into 1 by 2. Multiplying 2 inside, we get root 3 minus I is the first root when k is equal to 0. Next, if it's pi plus 4 pi, k is equal to 1 by 6. This is cos of 3 pi by 6, which is equal to cos pi by 6, similar cos pi by 2. Similarly, the next term will be sin pi by 2. So we can write here when k is equal to 1, we get 2 times cis pi by 2, which is equal to 2 into cos pi by 2, 0, plus I sin pi by 2 is 1. So this is equal to 2y. The next root is 2y. Next we take when k is equal to 2. When k is equal to 2, we get 2 into cis of 8 pi minus pi. So that is 7 pi by 6. 7 pi by 6 can be split further. It can be written as plus pi by 6. Pi plus pi, theta lies in the third quadrant. It can be written as 2 into minus cos pi by 6. Third quadrant, cos is negative. Sine is also negative. So minus pi by 6. The value gives us this is equal to 2 into minus root 3 by 2 minus I 1 by 2, which is equal to, multiplying 2 inside the bracket, we get minus root 3 minus I is the third root. Now the roots of Ez or the values of Ez are root 3 minus 1, 2y and root 3 minus I, 2y and minus root 3 minus I. Next question, another simple question and important. Let us first write what are the given equations. Given 2 cos alpha is equal to x plus 1 by x and 2 cos beta is equal to y plus 1 by y. Now let us simplify both the equations. This equation can be rewritten as take the LCM, see what is the value for x here. So here 2 cos alpha is equal to x plus 1 by x given. Now this can be written as 2 cos alpha is equal to x square plus 1 by x, or this is 2x cos alpha is equal to x square plus 1, or this is x square minus 2x cos alpha plus 1 is equal to 0. It is a quadratic equation in x here. The x is equal to, we know it is minus b plus or minus root of b square minus 4ac divided by 2a. So here what is a here? A is equal to, according to this equation, coefficient of x square is a is 1, b is equal to minus 2 cos alpha, and c is equal to 1. Substituting all these values, we get x is equal to minus b. So 2 minus of minus gives us 2 cos alpha plus or minus root of b square. 2 cos alpha whole square is 2 cos square alpha minus 4ac, 4 into 1. So this is 4 cos square alpha minus 4 whole divided by 2a, that is 2. Now we get this is equal to 2 cos alpha plus or minus root of cos square alpha minus 1 is minus sin square alpha. Taking 4 out of the root gives us 2 divided by 2. Dividing throughout by 2, this 2 gets cancelled. We get here, this 2 is there, gets cancelled, divided by 2. So we get cos alpha plus or minus sin alpha, taking out of the root into root of 1 minus is there, so becomes I. So here, this equation, the given equation can be simplified, which gives us this equation. From this equation, we get is equal to cos alpha plus or minus I sin alpha. Similarly, from this equation, solving the equation with the same procedure, we get y is equal to cos beta plus or minus I sin beta. Now the question is very simple. We are asked to find x power m by y power n minus y power n by x power m is equal to 2i sin m alpha minus n beta. Now alpha we take only the positive root from both the equations, so I write it as cis alpha divided by cis beta. Therefore, I want the value for x power m by y power n, which is equal to cis alpha whole power m divided by cis beta whole power n, which is equal to cis m alpha divided by cis n beta. Now this is equal to, we know that argument of z1 by z2 can be written as argument of z1 minus z2. Therefore, cis of m alpha minus n beta. Now this is nothing but equal to cos of m alpha minus n beta plus I sin of m alpha minus n beta. This is equation number 1. 4. Y power n by x power m is the reciprocal of this equation. This is equal to cos m alpha minus n beta minus I sin m alpha minus n beta. Now what is our question? What should we do with both these equations? Therefore, we want x power m by y power n minus y power n by x power m. Minus gives us plus m alpha minus n beta. So the cos terms gets cancelled. What is that remaining here? Now this is equal to 2 times I sin of m alpha minus n beta. This is equal to x power m by y power n minus y power n by x power m. Now the second equation is x power m into y power n plus 1 by x power m y power m. So we have found what is x power m y power n. We know what is x and y here. So now we are going to for x power m y power n will be is equal to cis alpha whole power m into cis beta whole power n. Now applying De Moivre's theorem, this is cis m alpha. Cis is cos alpha plus I sin alpha into cis n beta. This is product of two complex numbers. So Z1 into is product of two complex numbers. So the argument values can be added. So this is m alpha plus n beta. This is equation number 1. Next we want 1 by x power m y power n. Equation number 1, this is cos alpha cos m alpha plus n beta plus I sin of m alpha plus n beta. Now when I want the reciprocal of this value, this is cos of m alpha plus n beta minus I sin of m alpha plus n beta. This is equation number 2. Now adding 1 and 2, we get x power m y power n plus 1 by x power m y power n. This is equal to, adding this plus and minus term will get cancelled. We get 2 times of cos here. So this is 2 cos of m alpha plus n beta. So hence proved. Given z minus 1 the whole cube is plus 8 is equal to 0. This can be written as z minus 1 the whole cube is equal to minus 8. Multiplying by minus on both the sides, this can be written as 1 minus z the whole cube is equal to 8. Now, this again can be written as 1 is equal to 8 whole power 1 by 3 into 1. Now this is equal to 2 cube whole power 1 by 3. I take 1 here. This is 1 to the whole power of 1 by 3. Now this is equal to 2 into 1 power 1 by 3. Now there are three roots for the given equation. We know the cube roots of unity. We have learned what are the cube roots of unity. So cube roots of unity, that is equal to 1 whole power 1 by 3. The roots are 1 omega and omega squared. So we are going to substitute that here. This can be written as this is equal to 2 into 1 omega omega squared. Now multiplying by 2 inside we get 2 omega squared. Left hand side we have 1 minus z. I want z here, so z can be written as taking 1 minus 2 omega squared, which implies z values are minus 1, 1 minus 2 omega and 1 minus 2 omega squared. This is what asked to prove. Minus 1, 1 minus 2 omega, 1 minus 2 omega squared from the question.